So lesson 4, the heading is problems that involve momentum and energy. Little note, you can draw an arrow involving momentum, collision, and energy. Change in height. Is there a change in height? Is there a change in speed? Elijah, that's a job for conservation of energy. Is there a collision? That's a job for momentum. Is there both? This is a job for both. The first example we actually did at the tail end of our last lesson on conservation momentum. We said, okay, fire a bullet into a block, they stick together and they move off together. And that's cool, but I'm not, in fact, I did the same numbers. I'm not going to redo that one there. I didn't realize I typed the question in twice. And then on the next page, there's a lovely little section on types of collisions, and we already did that too, strangely enough. I'll get my notes organized next year. But what I want to get to is on the back of page 1, what's called the ballistic pendulum. Change in height. Right? The ballistic pendulum. A pendulum is a weight hanging from a piece of string. In fact, that weight has a name. It's called a pendulum bob, like the person Bob. It's called a bob. And here's what we're going to say. We're going to hang this weight from the string, and we're going to fire a bullet into it. They're going to stick together. They're going to move off together, but because they're on a string, it's going to start to swing up. It seems to me, if we're clever, if we know how high it swings, we can work our way all the way backwards and find out how fast the bullet was traveling. And this is how it was done before the invention of radar. Because there was no way you could stopwatch time a bullet and get the speed. You needed some kind of a system that could remove human reaction time. And so the ballistic pendulum was designed. Once radar came along, yeah, we don't do it this way anymore, but it's still nerdily cool. So read along with me. It says this: a bullet of mass that is traveling at 330 meters per second. It strikes a wooden pendulum bob of mass big M 0.85 and sticks. How high will the bullet and the pendulum bob swing? The trick to doing this is to realize you're going to divide the question into two parts: the collision and then the swing. You're going to divide it into the collision and then the swing. Is there a collision? This is a job for conservation momentum. Is there a change in height? Afterwards, that will be a job for conservation of energy. Collision. Before the collision, what's moving? Little m, big M, or both? Momentum of little m, initial. Wham! They collide. After the collision, what's moving? Little m, big M, or both? Stuck together or separate? So it's going to be little m V1, well, V little m initial equals M plus big M V final. I guess since there's only one initial velocity, I can just put V initial, and that'll be less yucky. And what we'd like to do is we'd like to find V final. We'd like to find how fast they move off after the collision. Why? Because that's going to tell us how much kinetic energy they had. And I think all of that kinetic energy, when they swing up, is going to turn into what type of energy? Potential, because at the top of the swing, how fast will they be traveling for a split second? 0. And even though it's a curvy path, for energy, we don't care, because energy is a scalar. Ooh. I think V final is going to be M V initial divided by little m plus big M. Little m, .005, 330, divided by 0.855. I think that's what you get when you add 0.005 plus 0.85. Yeah? With what speed do they move off after the collision? Do you get 1.9298? 2, 4, 5, 6, 1? Yeah? I'll go 1.9299, since this isn't my final answer. In fact, I'll keep this on my calculator. So I'll go 1.9298, not 99. 1.9298 meters per second. So they collide, and they start to swing off. Is that a change in height? Why, that's a job for conservation of energy. Does this question mention heat or friction or anything like that? Then, are any of these 0? Let's decide that we're starting, because we said the nice thing about conservation of energy is you can make ground zero whatever height you want. Let's put it at the height of the pendulum to start out. And, oh yeah, coming to a stop. So this is going to be a half mass of both V initial squared equals M both GH final. A half mv squared equals mgh. Oh, ha. Is there mass in everything, Riley? Well, that's convenient. Nice. Wait a minute, Mr. Duick. I don't know V initial. All I found for the collision was V final. Isn't V final after the collision going to become V initial once it starts to move? Ah. What am I trying to find? Oh, let's get the h by itself. How? Divided by g. In fact, I think we saw this last unit. We often had h equals V initial squared, and then I usually wrote it, instead of a 1/2, I just stuck a 2 in the bottom because that looked cleaner. It's going to be 1.9298 squared divided by 2 times 9.8. Hakeem, conveniently, I still have this number on my calculator. Squared divided by, you know what 19.6 is? 2 times 9.8. What about the negative? Hey, we're back in energy now. We're scalar land now. Yes? I don't want a negative height. And I get 0.19 meters, 19 centimeters. Yeah, enough who can measure that. Okay? Now, William, my friend, supposing I gave you this height instead, could you calculate what you needed your initial velocity to be? Could you work this backwards? Yes? And that would be this velocity right here, yes? So supposing you knew this, could you calculate the initial velocity of the bullet if you were working your way backwards? That's how it was done. You would measure the final height carefully, or you would use film, a photographic plate exposing the film, and even if it was a smear, you would just find out how high the highest point of the smear of the pendulum went, and you could get that very accurately, measure that nicely. You'd put some kind of a graph or a grid behind it, just like they do in Mythbusters very, very often, so you could see how high it went, and zip, 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 zip. Fairly simple calculations. Oh, that's how fast the bullet must have been going. And you were pretty accurate. You'd need the mass of the bullet. Oh, they probably had charts for that, or you just weigh the bullet. You need the mass of the block. Okay, this is a little bit inaccurate because technically, actually, over here, there is some heat generated on impact. I've seen when bullets go into wood, they actually char the wood behind them as they go in. You could probably take that into account if you did some careful measurements and be even more accurate. Certainly far better than starting and stopping a stopwatch trying to time a bullet by hand. So, let's try that. A 5-gram bullet is fired into a ballistic pendulum. Same diagram as on the previous page. If the bob has a mass of 2 kilograms and the bob rises a vertical distance of 8 centimeters, how fast was the bullet going? Swing, collision. And I wrote them in the different order this time because this time I think we know the after, the swing, and we're going to be working our way backwards. Is that okay? So for the swing, that was a change in height. That would have been a job for conservation of energy. We would have said this. We would have said on the swing, the final kinetic is 0, the initial potential is 0. We would have said, well, that's going to be a half m v initial squared equals m g h final. Zach, we would have smiled and said, woohoo! I said, woohoo! Woohoo! Oh, Zach. This time, Jordan, I know the final height. What I'd like to know is the impact, the velocity after impact. I'd like to know v initial, which I think is going to be vi. I think I'm going to times by 2, and then square root. It's going to be 2, 9.8. Careful, 8 centimeters. I'm not putting an 8 in here, Dylan. What's 8 centimeters in meters? 0.08. What's the initial velocity of the swing? 2 times 9.8 times 0.08. Square root of that. 1.2522 meters per second. Now, let's look at what happened before we started to swing. There was a collision. Before the collision, what was moving? Mass 1, mass 2, or both? Mass 1 stuck together, or, oh, just mass 1. I guess that's a dumb question to ask. Mass 1, so momentum 1 initial. Bam! They collide. After the collision, both stuck together. So this is going to be m1 v initial equals m1 plus m2 v final. Now here, direction and vectors matter, but here's the nice thing. My initial bullet was traveling horizontally. Right when the pendulum starts to move, which way is its initial velocity for a split second still? Horizontally. See, for a split second, our vectors still line up. So we can use vectors here. A split second after, we have to go scalar because now it's traveling upwards at an angle, but that's okay. The momentum part of the situation is taking care of itself already. What are they asking us to find here? Oh, VI. I think VI is going to be M1 plus M2 V final divided by M1. It's going to be 5 grams, 0.005 plus 2. Uh-oh, V final. I only have, I was going to say I only have V initial, but V initial for the swing, I think, was V final after the collision. Yes? So 1.2522, all divided by mass 1.005. So if you were a RCMP officer 100 years ago, you could have calculated the muzzle velocity. I feel the same way. Oh. 0.005 plus 2 times my answer that's still stored in my calculator divided by 0.005. 502 meters per second. Yeah, it seems okay as a legitimate answer. Bullets go fast. Example 3. I wrote here, in designing a ballistic pendulum, you want a bullet of mass 6 grams and a speed 6 times 10 to the second 4. Okay, I don't think that 4 should be there. Scribble that out. To make the pendulum bob rise 3 centimeters, what mass must the bob have? Well, let's go back to this original situation here. If you knew your height and you knew your speed, could you actually figure out what mass you wanted it to have? Yeah, you could solve for big M. Meh, Sean, I'm not going to bother. Instead, let's do some roller coasters. A 3-kilogram car traveling at 18.5 meters per second collides with a stationary 2-kilogram car on a frictionless track. The cars stick together and move off. What combined height do the cars reach up the next hill? Is there a collision? This is a job for momentum. Is there a change in height? This is a job for conservation of energy. Which happens first, the change in height or the collision? So let's do collision, then let's do change in height. Collision, delta H, change in height. Okay. Before the collision, what's moving? Mass A, mass B, or both? So momentum of A initial, when they collide. That's how Zach would say it. When they collide. After the collision, what's moving? Mass A, mass B, or both? Stuck together or separate? So I think it's going to be mass A, V initial equals mass A plus mass B, V final. In fact, I'm thinking this through. This is going to be almost exactly like the ballistic pendulum, except we're on a track. But I think the physics is going to be identical. The vectors don't care. The scalars don't care. I think V final, after the collision, is going to be mass A, V initial, divided by mass A plus mass B. It's going to be mass A, 3, V initial, 18.5, divided by both, 5. Oh, holy smokes, that works out nice. 11.1 meters per second. They now move off. It's frictionless, William. We're in our magic physics world, so we don't lose any energy to heat. But William, is there a change in height? Yeah. And also, do you notice it's a curvy, yucky path? I mean, if it was straight up, we could use actually free fall and unit 1 kinematics to actually also calculate the height, because we know the acceleration is negative 9.8. But it's when you have a yucky, curvy change in height, this is where conservation of energy really shines. This is where conservation of energy saves you work. No pun intended? Come on, people. Okay. Work, energy. Tip your waitress. Tough audience. Any of these 0? Oh, and Matt, sadly, this is my daytime job. Go ahead. Any of these 0? Elijah's squinting and thinking. Which ones? Darn right, starting out on the ground. Yep. This is exactly like the ballistic pendulum, actually. Cool. It's going to be a half m v initial squared equals m g h final. Which mass? Well, it's the mass of both, but do I really care? What happens to the masses again? Cool. And, oh, yeah, Mr. Dewick, this is exactly like the ballistic pendulum. It's going to be VI squared divided by 2G. It's going to be this number squared divided by 2 times 9.8. Why not negative 9.8, Mr. Dewick? Energy scalar, we don't care. Squared divided by, bracket, 2 times 9.8, or 19.6 if you can do that in your head. And I get 6.3 meters. .3 meters. Oh, that's a part B. All right, let's put our thinking caps on. The steepness of the slope is decreased as shown below, so the slope is shallower. With this decreased slope, the combined cars will reach a lesser height, the same height, or a greater height. You know what? Since there's 3 answers, I think once again, let's do we'll vote by how high you hold your hand up to indicate your certainty. So we have first answer, second answer, or third answer. If we decrease the slope so the hill is not as steep, who says the first answer is not going to go as high, lesser height? Who says the second answer, same height? 4, 5, 6, 7, 8, 9, 10, 11. And then we have Jordan, who jumps on the peer pressure bandwagon to make it 12. Who says a greater height? 1, 2, 3, 4. Okay, convince me. Someone's wrong. Someone's right.
I'd say greater height because it's not the slope isn't that steep anymore, so it's not, you can use more energy to go up and go further.
What direction is the force that you're resisting when you go up a hill? It's gravity. What direction? Dead vertical. Dead vertical. Whether the hill is steeper or shallower, I think you're still going to use the same amount of potential energy. I think, in fact, I know, the answer is actually the same height. Now, Matt, shallower would take you longer, yes, to get that high, which means you'd need less power. If you were walking it, you wouldn't be as tired. Steeper would be you get to that height faster, which means because power is work over time, since the time was shorter, you'd feel more tired, but you would have used up the same amount of potential energy. And this is why I went on that big rant in the energy unit. Work energy is not tiredness. Tiredness is actually power. When you get tired, it's because you had to create more power than your body was comfortable with, not that you had to do more work than your body was comfortable with.
If there was a force of friction.
If there was friction, that would probably change things. Yeah. But we're in our magic physics world, so we're good. Example 4. A roller coaster car of mass 225 kilograms is at the top of a 6.5 meter high hill, traveling at 8 meters per second. It rolls down the hill onto a level track and strikes an identical stationary car. The two cars stick together. How high up the next hill will the two cars roll? This is the same as the question we just did, except I've added an extra hill here. So here's car 2, here's car 1. And then they'll roll off together up a hill, and we want to find height h. How fast is car 1 traveling right now? Eight meters per second. Is that how fast it's going to be traveling when it hits car 2? Why?
It'll undergo acceleration.
Are you saying there's a change in height? Are you saying that's a job for conservation of energy? In fact, you know what? Let's do this. I think we're going to have to, first of all, deal with situation 1. That's the change in height of car 1. Situation 2 is going to be, wham, they collide. Situation 3 is going to be, they move off together. I think this is going to involve 3 steps. Situation 1, is there a change in height? Is there a change in speed? Why, that's a job for conservation of energy. I can do that. I can't nuke anything else because its initial kinetic isn't 0. It's already moving. Its initial potential isn't 0. It's starting up high. And I would like to find V final. So I think I'm going to go like this. A half m V initial squared plus m g h initial equals a half m V final squared. Yay! And I'm going to do, what am I trying to find? What am I trying to find? V final. I'm going to do one more thing, Elijah. I'm going to go times by 2, times by 2, times by 2, because that's going to clear that fraction. That's going to clear that fraction. It is going to leave a 2 in front of the GH, but that's, I think, McKenna, much nicer than a bunch of halves kicking around everywhere. Is that okay? I got your name right? Those little things. So I think it's going to be V initial squared plus 2 GH initial equals V final. Wait a minute. How to get rid of squared? I think it's going to be the square root of this whole thing equals V final. V final at the bottom of the hill. How much room have I got? Oh, lots of room. Good, 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 good. Is going to be the square root of its speed at the top of the hill, 8 squared plus 2 times 9.8 times the height of the hill, 6.5. 8 squared plus 2 times 9.8 times 6.5 square root 13.8347. I'll write 13.8, but I'm going to keep that number on my calculator. And now, Hakeem, what I've done is I've turned it into this question, because now I know that velocity right there. How fast is it traveling before it hits? 13.8 blah, 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 blah. In fact, that's going to bring us to situation 2. Is there a collision? This is a job for momentum. Well, yeah. Before the collision, what's moving? Mass 1, so momentum 1. After the collision, what's moving? Stuck together. This is going to be M1 V initial equals M1 plus M2 V final. V final is going to be M1 plus M2. Oh, 225 plus 225. Oh, Mr. Duick, you're doing this wrong. Sheesh. I'm getting V initial by itself. Sorry, guys. V final by itself, I want to divide by M1 plus M2. Is that what you were thinking, Callum? Yeah, you were thinking that? You weren't just blindly writing stuff down with your brain in neutral? Because if you weren't, you wouldn't have to be erasing anything. Of course, it's going to be mass 1, 225. Velocity 1, 13.8, divided by 225 plus 225. Right? I wish I'd done that on purpose, but I know I had a brain cramp there. Times 225 divided by 225 plus 225. 6.9174. Now we move to situation number 3. How am I going to handle situation number 3? How do you know? You're right. Change in height, change in speed. Hey, this looks like a job, especially if it's a yucky, curvy path. Again, I should be careful, Tanisha. If it's straight up and in free fall, we were able to handle free fall actually at the beginning of this year already without conservation of energy. It's when it's at wonky, weird, curvy paths and angles, then conservation of energy really shines. So, situation 3. I think I can say kinetic energy final is 0 because it's saying, how high? Oh, and let's let the ground be 0 height. I think then, Riley, we're going to get a half m v initial squared equals m g h final. This is getting kind of routine, Mr. Duke. Good. Hey, if this is becoming familiar, we're understanding the laws of the universe. Once again, Michael, the masses cancel. By the way, it is technically, Nate, the mass of both, but I don't care. So when you're designing roller coasters, now I've been looking, bumper cars have lots of collisions, great conservation momentum. I have yet to see any ride that combines a roller coaster and a bumper car, so this is a purely theoretical. But certainly, if you remove the collision part, definitely when they're designing roller coasters, they would make sure that this velocity over here was enough to make it up the next hill. In fact, that's all that first chain does when you go on the roller coaster. All that first chain does is it gives you a whole bunch of potential energy, and all you do is you spend the rest of the ride converting it into kinetic, back into a little bit less potential, back into a little bit less kinetic, back into a little bit less potential, a little bit less, because you're losing some to friction the whole time, and eventually the ride brings you to a stop. Blah, 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 subtract the 3, carry the... Oh, h final. Final height is vi squared divided by 2g. It's going to be 6.9174 squared divided by 2 times 9.8 squared divided by 2 times 9.8. 2.44 meters. I think this question is tougher than I'll ask on the test because there's 3 things. I think as a nasty, I would be okay on your test giving you one of the previous questions. So the ballistic pendulum, either here's the initial speed, find the final height, or here's the final height, go back and find the initial speed of the bullet. I think that's kind of nerdily cool. Or the roller coaster colliding and how high up the hill they go. But I don't think I'll give you in Physics 11 top of the hill, bottom, then top of the hill again. Okay? But there's some examples of questions that combine both energy and momentum. I think you can do some neat applications. What's your homework? Well, quiz 1. When's your test? A week Thursday. So you can expect then I'll be giving you 2 great big reviews this Thursday. We'll also be marking quiz 1 this Thursday. We'll also probably go over the work energy test, since you'll notice there is some overlap between work energy and momentum. It's conserved. Friday, I may just say work on the reviews. I may start the next unit. Or Tuesday, I may just say work on the reviews, start the next unit. We will be starting the next unit. We'll get 1 lesson in, and that'll lead up to your test. Next unit is looking at vectors and vector math and projectiles and how we deal with all of that. Lots of trig. Officially, as far as I'm concerned, I got about those count them 2 units left, roughly. But maybe 3 if I can get to relativity, which would be nerdily cool.